Welcome to a Project Radium workflow demo showing how easy it is to work with existing containers. This is a tech preview and represents no commitment to deliver the features shown. Project Radium virtualizes devices on remote machines for clients needing acceleration services, primarily for machine learning applications. Project Radium uses a general approach, monitoring system and memory events. It is not specific to any device, vendor, or API. This demo highlights a workflow that is convenient to data scientists, a flow with no unexpected steps. Pull your image, add it to the Radium cluster, and run your application. In a way, we are demonstrating what you don't have to do with Project Radium. Radium performs the error-prone work behind the scenes. Under Project Radium, a machine learning application can use a remote GPU that is allocated from a pool just for the dynamic runtime of the app. The machine that launches the application is called the initiator or client. In this demo, we'll call it the client. The remote machines with the GPUs are called the workers, or sometimes the acceptors. The workers run the parts of the machine learning application that require GPU access. Project Radium splits the application appropriately and maintains coherency between nodes. In addition to the clients and workers, there is a Radium manager that serves API requests from clients, manages the whole cluster of client and worker nodes, and keeps a database of configuration and utilization data. Radium works with containerized applications. It uses containers on both the client and worker nodes. Before we show you the actual workflow, let's look at the workflow that Radium avoids. In this hypothetical inconvenient workflow, a user must create a new container image to install Radium on top of a base image. This can be error-prone and has to be redone every time the base image changes or Radium has an update. Next, the data scientist must log into the worker nodes and pull the new image. This infrastructure, each worker node, is usually owned by the IT team, not the data scientist. What we will demonstrate instead is a workflow entirely on the data scientist's own machine, the client. Here, we have a minimal Radium cluster with a single client, a single worker, and the manager. In our case, we'll happen to run the client and manager on the same VM named Developer Test, and we'll run the worker on a VM called Romeo, which has an NVIDIA T4 GPU. First, the client will add the image to the Bitfusion cluster. Second, the client will pull the image for itself. Third, the client will run the containerized application. Now, behind the scenes, Radium will take care of two things. One, the manager will ensure that workers pull the image. Two, it will mount the Radium libraries in the containers and launch any application as a Radium process. Now, we are on the actual screen showing the manager, worker, and client shells. In the upper shell, we see the manager is already running. On Romeo, on the right, we start the worker service. In the client pane on the lower left, we define a global variable with the URL of our base image, a TensorFlow image from the NVIDIA NGC library. We next run a client command to add the image to the Radium cluster. You can see messages in the manager that the image is being added and workers are told to pull it. And on the worker, you can see the image being pulled. This typically takes a few minutes. Next, back in the client pane, we pull the image for the client itself. It completes instantly here, since we already pulled the image before we started recording. Now, Let's run a very simple TensorFlow workload on the client. All it does is sum up a million random numbers, easy enough for a GPU. We use the unmodified NGC container. We automatically mount the Radium libraries. A special entry point detects the Linux distribution, allowing us to use the correct Radium libraries. All of this is transparent to the user who merely runs the workload command. The workload now completes. It prints out the average value of our random numbers was about 42, as we requested at launch. Now we will run an actual TensorFlow benchmark. It is a simple training exercise using the MNIST dataset. From the code here, you can see it creates a simple model and reports how fast we can train it. To run it, we specify the image and use flags similar to Docker run. This time, we'll watch the GPU utilization on the worker, Romeo, as the app runs. Here, GPU memory is allocated. And here, GPU utilization is shown in the teens. The benchmark completes after 5 epochs or walks through the dataset, and it reports about 3 seconds per epoch. We've kept the workflow about as simple as working with a local GPU. Pull your image, add it to the cluster, and then run your image with familiar arguments. Thank you.